My name is Jordan Smith, and today we'll be talking about velocity, or more specifically, constant velocity. We'll describe constant velocity through models, such as this one, some videos, such as these, and some good old classical kinematic equations. To start, we must discuss what we would define as constant velocity. Constant velocity is achieved when there is no net force acting upon the object in motion, as stated in Newton's first law of motion. As the name states, velocity would have to stay the same within the given time intervals. So, using that exact law, we filmed a video showing us rolling a ping pong ball across the surface for approximately 0.55 seconds. With this, we used our software tracker to track every single individual point where the mass, which is our ball, moves across the x-axis. After finding this video, we were able to gather some information. We started with the observation start time of 0 seconds. The ball's initial position was negative 0.013 meters in the x-axis, 0 meters in the y-axis, and 0 meters in the z-axis. The ball's initial velocity was 0.882 meters per second in the x-axis, 0 in the y, and 0 in the z. As I stated before, we only observed the ball for 0.55 seconds. Now we're able to use VPython as a computational model. First, we ported over our information of our ball's position vector and our ball's velocity vector, as you see highlighted here. We set our delta time to change each time step to be 0.17 seconds. We also ported over that our time is 0.55 seconds. As you see, our F net is 0. Our ball's velocity was put in here thanks to the momentum principle, and our ball's position vector was placed here. Our ball's position is updated by the ball's velocity times the change in time. That's our object's position. And our object's velocity is calculated by the net force times the ball's mass times the change in time, which ends up canceling out to be 0. Now you're about to see us run the computational model. As you can see, that graph is very similar to the one that we saw before in Tracker. To see how close the velocity is between the computational model and the video, I used an Excel spreadsheet to model the velocity throughout every interval in the video's time. As you can see, the lines are very close to each other. Now we are asked what would have happened if I would have changed the orientation of the axes. The answer would be that the velocity would still be the same. However, the positions of each of the vectors would change. The velocity would still follow a completely straight trajectory, showing that constant velocity is still possible, regardless of how I would have positioned the axes.